Hi, and welcome to 7.3 Apparent Weight. In this lesson, students will be able to define apparent weight, and students will be able to describe how to create artificial gravity. What? So this is the definition of apparent weight. The apparent weight of an object is equivalent to the normal force acting on that object. So just think about this. If you have a person standing on a scale, and they're at rest and nothing else is happening, then you do have this, downward force due to gravity. And you also have an upward normal force between like the feet and the scale. So the scale is actually telling you what the normal force is. It's reading how much your feet are squeezing against the scale. And they're squeezing against the scale because of gravity, right? But the scale doesn't know that. It's just saying, oh, there's some kind of force there. I'm reading out a normal force of however many pounds or newtons. And that is your apparent weight. It's the normal force. And we've already discussed how, sometimes your normal force isn't actually equal to your weight. You could change what your normal force is depending on the situation. If you're at rest, they're equal to each other. But it says the apparent weight of an object can differ from the force due to gravity if the reference frame is accelerating. So instead of this person being at rest on a scale, maybe they're accelerating. Maybe the room they're in is accelerating. This difference is due to the object's inertia because the person has inertia. Right now they're at rest. But if the floor starts accelerating upward towards them, they're at rest and they want to stay at rest. So they're like, no, I want to stay here. And they get squished into the scale more because of their inertia if this starts accelerating upward. So that's the idea there. So an example would be an accelerating elevator. So in this first scenario, we're going to move the elevator at a constant velocity. So in the previous example I gave, you were at rest and the forces were balanced. Well, if you're moving with a constant velocity, the forces are also balanced. So in that situation there, the scale that the person was standing on in the elevator would have read out what it normally reads out. But if if the elevator is accelerating upward because of the person's inertia, they're going to resist that and it gets squeezed into the floor more. And if you were in an accelerating reference frame like that, the scale that you're standing on will read a higher value than what it normally does. So you're being pushed into the floor more in that accelerating reference frame. Okay, so knowing that, think about this. Is it possible to make artificial gravity in a spaceship or space station? Why or why not? Consider what you've learned about circular motion, centripetal force, and centrifugal force. If you were going to design something where you just have to push a button and all of a sudden there's gravity in outer space, how would you do that? Pause the video and think about it. You might have thought about some things that you've seen in sci-fi movies. So this is from Interstellar, and there's a whole scene where he like basically pushes a button here, and then the whole thing starts spinning around. Now, why would that cause gravity? What do you think? If it's spinning, what does that mean? Hmm. So here's our situation. Instead of the person being in an elevator, now this circular thing here is our space station. All right. So we're going to spin the person around. Whoa. Okay, now why did that person move in the circle? What was causing them to move in a circle? A centripetal force. And what kind of force is acting as the centripetal force in this situation? What kind of force is it? Is it tension in a string? Is it gravity? Is there a gravitational pull between some No, none of that. It's actually the normal force between the person and the floor that they're standing on. So this floor here exerts an upward force on the person, and the normal force is acting as the centripetal force. So it's the normal force. The normal force is causing you to move in the circle. And what did we just learn about the normal force? Your apparent weight is equal to the normal force. So this person feels like they're being squeezed into the floor in that situation. And that's what it feels like when you're standing on Earth. You're being squeezed towards the center of the Earth. So that effect makes them feel like there is artificial gravity there because there's a normal force between their feet and the floor, which is kind of cool. Now think about this. That if there's a normal force, that means there's a centripetal acceleration, right? Because the normal force is acting as the centripetal force, which is acting as the net force. The centripetal force is the net force, and the net force is equal to the person's mass times their acceleration. Now, here's a question for you. If you were designing this space station, what should the magnitude of the centripetal acceleration be? What would you want that acceleration to be? What do you think? You would want the centripetal acceleration to be equal to 9.8 meters per second squared. If that's equal to 9.8 meters per second squared, the centripetal acceleration, that means you've effectively created 1g, they call it 1g of gravity. And there you go, artificial gravity. If it's spinning slower, if it's less than that, then you're gonna feel lighter. If it's spinning super fast, you're gonna be squeezed into the floor even more, and your acceleration will be higher than this if it's spinning super fast. And you're gonna feel very heavy because of your apparent weight. So that's kind of the gist with apparent weight and space stations. People have thought of this before in the 1970s. This is art. It's a space colony art from NASA Ames Research Center. So this is, a huge space station with like forests and trees and like cities and everything. The whole thing is spinning around, creating artificial gravity. You might have seen this before. Here's a view from inside of what the artist rendering of what could possibly be in the future might look like. And I think it's kind of cool that they had glass up here or whatever it is, some kind of clear material so you could look out. And if you just look up, you see the ground above you, which is kind of crazy. All right, so that's pretty cool. I've never seen this movie, but Elysium in 2013 had a big structure like that in it. And on a smaller scale, you have The Martian, and then I already showed you that screenshot from Interstellar, but this one is from The Martian, and I like this picture here because you could see the person here, and then the person standing here, and this portion here is this portion here. So this, if you've ever seen that movie before, this ring is moving in a circle the whole time. So this person here is just standing on the floor and moving in a circle and this person is not, so they just see them spinning around, but also standing up in the artificial gravity. That's really just because of the centripetal force, which is being provided by the normal force between the person's feet and the floor. Pretty cool physics stuff. So let's do some math. I mean, that's pretty cool physics stuff, right? Let's do an example problem. It says a 75-kilogram astronaut is in a spinning space station that has a radius of 100 meters. Their apparent weight is 400 newtons. Okay, so they're in the space station, as shown here, and their apparent weight is 400 newtons. They feel like they're 400 newtons. So the questions are, what is the normal force acting on the astronaut? What is the centripetal force? What is the centripetal acceleration? How does their apparent weight compare to their weight on Earth? And should the space station speed up or slow down to achieve a more accurate artificial gravity? And how fast should the space station spin in order to achieve 1g? And in this situation for part F, we're just looking for the tangential velocity. There is a whole unit in physics called rotation, where it's like, okay, well, how many rotations per second are you doing? We're not doing rotations per second. We're just saying, okay, what is the tangential velocity at that point? Okay, so let's do, if you want, you can pause the video and try to figure this out on your own. But I'll show you how to do it here. So I like to write down the given information first. Now we're not on Earth anymore, so I can't say that G is equal to 9.8 anymore. We actually don't know what the G's are that they're feeling. But we do know they say their apparent weight is 400 newtons. So it's in newtons, so I know that's some kind of force. All right, but what type of force is that? Well, it's a circular space station. What type of force is acting as the centripetal force? We already kind of alluded to it earlier, so I won't belay it because I already explained it. It says, what is the normal force acting on the astronaut? Well, their apparent weight is equal to the normal force. And that's the thing that's moving them in a circle. So part B, what is the centripetal force? It's the normal force. The normal force is the force that acts as the centripetal force in this situation. All right, so part A and B are done because they're really just like leading you into part C. Part C says, what is the centripetal acceleration of the space station? So now that we know, oh, their apparent weight is 400, that's the centripetal force, actually. Now we could calculate the centripetal acceleration. So this is what's in your reference table, but if you want, you could rearrange it to solve for the acceleration. Because after all, this is still just Newton's second law. The net force, or the centripetal force, is directly related to the acceleration, and the mass is inversely related to the acceleration. So Newton's second law still holds true. Now the acceleration is equal to 400 newtons divided by 75 kilograms. So let's see, what is the centripetal acceleration of this space station? We want it to be what number? What do we want the acceleration to be? We want it to be 9.8. Let's see. This is only 5.3 repeating meters per second squared. So it's not as much acceleration due to artificial gravity as you would have on Earth. So you would feel a little bit lighter. Part D says, how does their apparent weight compare to their weight on Earth? Well, first we have to figure out what is their weight on Earth. So I'm going to do down here. Still, this good old formula here, we're looking for what their weight on Earth would be. So now we can use that 9.8 meters per second squared. And if you want, you make it negative to say, oh, well, the weight is pointing in that direction. So on Earth, this person is 735 newtons. Normally, when they're standing on the surface of Earth, they feel 735 newtons pushing back up on them, supporting them. Yeah, so that's not what they have now, though. They only feel 400 newtons, so they feel less squeezed into this circular space station. Okay, so that's what's going on there. Do you feel, stand up and feel the squeezingness between your feet and the floor? Kind of a cool thing to do if you're a physics nerd. So part E says, should the space station speed up or slow down to achieve a more accurate artificial gravity? We want this to be closer to 9.8. So we want the acceleration, it should be greater. We want it to increase. So what is the relationship between speeding up, that's velocity. What is the relationship between velocity and acceleration, centripetal acceleration? AC is equal to V squared over R. Now, our goal is to have the acceleration increase. We want this part to go up. So what should we do to the velocity in order to make the acceleration increase? Should we increase the velocity or decrease it? So hopefully you could see it is an exponential relationship. So if you increase the velocity, then the acceleration will increase. So part E will just say that it should speed up. More velocity, please. Okay. And then for part F, it says, how fast should the space station spin in order to achieve 1g? So now our goal, we want the acceleration to be 1g. We want it to be 9.8 meters per second squared. Let's make our centripetal acceleration of the space station 9.8. Well, the radius is 100 meters. So it says, find the tangential velocity that would make that true. And we're going to use this equation here. All right, and then you can solve for V if you want, or just plug in the numbers. And you should get a velocity of 31.3 meters per second. So on this rotating space station, we want the tangential velocity over here to be 31.3 meters per second. Now, we're not really saying what they call it angular velocity or rotational velocity. How fast is it spinning? How many rotations per second? We're not saying how many rotations per second. That would be good to know. All right, but for now, we'll just say, okay, well, the tangential velocity at that point should be that when you have a radius of 100 meters in your awesome space station. Okay, time to test your mettle here. Can you do this practice problem? Pause it, read it, do it. It says, okay, did you pause it? I'll read it to you. It says, an 85-kilogram astronaut is in a spinning space station that has a radius of only 25 meters. How fast should the space station spin so that their apparent weight matches their weight on Earth? We're really looking for what the tangential velocity should be at this 25-meter mark, okay? So it says, what is their weight on Earth? These are designed to help, it's like scaffolded. It's helping you guide to get this answer. All right, so you have to do these parts first. Well, you don't have to, but it helps you. A, what is their weight on Earth? What should the normal force or centripetal force be? What should the centripetal acceleration be? Think about this one. All right, what should the tangential velocity be? And how long would it take for the space station to rotate once? All right, pause the video here, try it out, and then we'll go over it. Okay, so the first thing I like to do is write down my units. We are looking for the tangential velocity, and the first question says, what is their weight on Earth? So Fg equals mg, boom, and I'm calling it negative 833 newtons because it's pointing down, right? When you're standing on Earth, the force acts in the downward direction. But no, we're not on Earth anymore. We are in a space station. So it says, what should the normal force be? Regardless of space station or not, the normal force is going to be upward. And on our space station, we want the normal force to be 833 newtons. So it says, what should the and then in parentheses, it says, what is the centripetal force? So yeah, we know now that centripetal force should be 833 newtons. But how do you make it 833 newtons? Let's see. What should the centripetal acceleration be? Oh, and by the way, boom, units -1 because I didn't write meters per second squared over here. So I'll write it here. All right, so don't forget to write your units when you're taking a test or quiz. Anyway, so this is the one I circled before. You might know what the centripetal acceleration is going to be, but we could calculate it. So the desired force is 833 newtons. And guess what? It's 9.8 meters per second squared because you're basically undoing the math that you just did to get the artificial gravity, right? We want 1g. So we want the space station to spin in a circle so that there's an acceleration, the centripetal acceleration of 9.8 meters per second squared. That is artificial gravity right there. So did we have to do this? No, we didn't have to do any of this stuff because we know it should be 9.8 meters per second squared. But it's like interesting to talk about, I guess, and you like listening to me. So it says the centripetal acceleration is equal to v squared over r. We're looking for the tangential velocity, plugging in our numbers. AC, this is, artificial gravity. The radius is 25. So the tangential velocity at this point on our space station should be 15.7 meters per second. You should be moving across at 15.7 meters per second, and that'll give you 1g, 1 Earth gravity. So it says, part E, how long would it take for the space station to rotate once? How long would it take? They're asking for the time for one rotation. The time for one rotation is the period. So we're going to solve for the period. We know what the velocity is and the radius at that point. So we plug in the numbers. Now be careful when you solve, right? You cross multiply. So then you have to do 2 times pi times 25, and then you have to divide by 15.7. I didn't show that, but I know some people are going to try to multiply. No, it's this divided by 15.7. When you cross multiply, you'll see. Anyway, the period is 10 seconds. So every 10 seconds, that thing has to make one rotation, And then you'll be pretty much like you'll feel like you're on Earth. You're standing on that spinning thing, and it's basically the same thing. You know, it's not just awesome that you're in space, uh, spinning around in the space station. Anyway, that's about it. Thanks for watching, and have a great day.